What is up, everyone? This video we are going to discuss infinite series. So previously we have learned what a sequence is. We we have learned infinite series sequences, right? So now we are going to learn infinite series, right? So we know that uh, an infinite sequence is a list of infinite numbers. So here a sub 1, so we have a list of numbers. So how many do we have? Infinitely number of values in this list. Alright, so this is a list of numbers. It has infinitely many values, numbers, right? So if you add up all these numbers, we get an infinite series. So if you add up all these numbers, so this is a general term, a sub n goes from 1 to infinity. So if you add up this list of numbers, you can generate a series, right? So this is called infinite series. Right? So now we are going to check whether this series is convergent or divergent. If this series is convergent, so what the meaning of converging this series is, the infinite sum of this list is if the infinite sum of this list is equal to a finite value s, then we say if s is a finite value, it's a real value, it's a real number. So if this one is finite, so or real number, then we say this series is convergent. If this infinite sum this sum is equal to infinity, then we say this infinite series is divergent, right? So I hope it makes sense to you, right? So we have learned list of numbers, infinite list of numbers, and this is called a sequence. If you add these lists up, then we can get an infinite series. So if you have an infinite series, you can talk about the convergence of that series. So if you say this one is convergent, that means this sum, infinite sum, should be equal to some finite number. Then we say this infinite series is convergent. Otherwise, or this infinite sum is equal to infinity, that means this one is divergent, right? Now let's consider, so we can define a partial sum. So here this is the infinite series, a1 plus a sub 2 plus this goes on, right? This goes on forever. Now I consider partial sum. First I consider this bit. I denote that one is s sub 1, and then I add first two terms only. S sub 2, and so on, right? So S sub 1 is the first term of the sequence, and S sub 2 is the first addition of first two terms of the sequence. S3, you add up first three terms of that sequence. Remember this sequence, right? So A sub 1, A sub 2, A sub 3, and this goes on. So you can define a general term. So this is the first partial sum, this is the second partial sum, this one is the third partial sum, and this one is the nth partial sum. Up to n. Adding all terms from 1 to n, then you get nth partial sum, right? So here, so in the note, if you look at the note, so it is provided. So the definition of nth partial sum is given. So if you have a series, infinite series like this, then you can define the nth partial sum. So can someone say, so what is the limit? So actually, this is also a sequence here. So this is your first term, second term also a number, third term also a number. You can say this is the nth term, general term, which is a number, sum of first n terms of the sequence. So this one also an infinite sequence. So what is the limit of this sequence? The limit of this sequence is the sum of this infinite series. So the limit of this infinite sequence is the sum of that infinite series. As n tends to infinity, that this series, we generated a sequence like this, S1, S sub 1, which is the first partial sum of this series, the second partial sum of this series, third partial sum of that series, nth partial sum of that one. So now we generated a sequence from this list, right? So the limit of this sequence, limit of these partial sums converges. The partial sum is said with the sum of this infinite series. All right. I hope this makes sense. This make more sense to you, right? So this is the connection between series and infinite series and infinite sequence. So both are the same. So series is also a sequence. Yeah. So this is your series. You can define partial sums like this. Then you can generate a sequence. The limit of this sequence is the same as the sum of this infinite series, right? I hope this makes sense to you, right? Let's look at an example. Find the partial sum S sub 1, S sub 2, S sub of this infinite series. So pretty easy, you can find the partial sums here. These are the partial sums. First term, second, so right, this is the partial sums of this series. I think you know these. And 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 you can write the general nth partial sum of this series, which is a geometric series. Wait a second. So S sub n is 1 over 2 plus 1 over 2 squared plus up to 1 over 2 to the n. This is a geometric series with a constant ratio 1/2, right? So the sum of this finite geometric series is A. So what is that? A is 1/2 and 1 minus your common ratio divided by 1 minus your common ratio. This one is same with this, right? So by taking limits, if you want to find this infinite sum, if you want to find the infinite sum, all you need to do is taking the limit. All you need to do is take the limit of this partial sum. So this becomes the sum of this infinite series. Your right hand side here, this goes to 0. Then this infinite series, the sum of this infinite series is equal to 1. Alright. Here look at this. You have a arithmetic sequence, arithmetic series. The sum of first n, so sum of this list of numbers is equal to n times n plus 1 divided by 2. So this is the nth partial sum of this infinite series. By taking limit, you know that this term goes to infinity. Therefore this is divergent, this diverges to infinity, right? And we can talk about geometric series. Here you have the common ratio is r. So a, you can, yeah, so if the common ratio in between -1 and +1, so this infinite series converges to this number, otherwise it is divergent, right? So here in the note there are a lot of examples provided, so you have to go through those examples to understand the content, right? So look at this number. This is the repeating decimal. So here 0.6666, this goes forever, right? This goes forever. This doesn't stop, right? This goes forever. So you can write, so this can be written as, so in this way, see, so you get this one here, this 0.6 given by this term, 0.06 given by this term, the sum of, so you get an infinite series like this. And you can find, so here this is a geometric series, then you can find the sum of that. So the common ratio is 1 over 10. which is less than 1, that means this infinite sum converges to a finite number, which is that. Here look at that, the sum of this infinite series is equal to 2/3. Alright. Here they do another example. This is also repeating decimals as 2, 5, 5 and 20, 2, 1, 2, 1, 2, 1, like that, right? So first one is 1.5, then other part can be written in this way, right? And this one also a geometric series, so you can find the sum of that infinite series like this very easily. So we can also talk about telescoping a series, and here, so here you have a bottom denominator is a polynomial quadratic second order degree 2 polynomial. You can split into partial fractions and do I think you have done this kind of thing in your school, right? So this one is known as the harmonic series, and this series is divergent. You can show that by writing nth partial sum, right? So here just, so first one is 1, second one is 3 1/2, and third one you can show that term fourth partial sum is bigger than 2, and eighth one, because this is a positive terms, so this is non-negative term, so you are adding up a positive terms continuously, right? So you can consider this one as 4 as 8, and so you can show that this one is true. So by taking the limit, so this goes as n tends to infinity, your right hand side of the inequality goes toward infinity, and that means this one also is going to infinity. That means this has some the partial, this is a so this is a subsequence of this. You don't need to think like that. So because this one is divergent, therefore this one also divergent, right guys, I hope this makes more sense to you, and that's it, um, today's lesson, and thank you.